Hello again. So far we have learned how to calculate a moment of distribution. In this video we'll learn about very important moments of a distribution, which we call them characteristic function, moment generating function, and so on. So the importance of these characteristic function is that from these moments we can get the distribution back. So basically, if you have for a random variable x, if you have the PDF or CDF fx of x, we can calculate any moment, mean of g of x, which is basically integral of g of x fx of x d of x from minus infinity to plus infinity. So this is applicable for any function g of x. Now, if instead of g of x I put some specific functions, we know about Fourier transform, Laplace transform, and so on. So we see that Laplace transform of, let's say, fx of x is equal to e to the power minus sx fx of x, let's say dx. This is integral from minus infinity to plus infinity. This will become a Laplace transform of fx of x. And we know that if the relationship between the PDF fx of x and Laplace transform is 1 to 1. So let's say I denote this one by L of fx of x. So this is a moment. So here, this is going to be your g of x. But this g of x has a parameter in it, in s, which makes it useful in the sense that using this moment, if I have the value of this moment for a sequence of values of s, then I could possibly get my distribution back. So you know that this is Laplace transform is an analytic function, and if you know the value of an analytic function for any converging sequence, you can calculate the expression or the value of the Laplace transform. So let's begin. So characteristic function is basically a Fourier transform of the distribution. The only difference is that in Fourier transform, people they put a minus, but in a statistical community they didn't put these minus. But mathematically it would have been more convenient to put minus, but historically they haven't put. So this is what we define as characteristic function. So basically, characteristic function is Fourier transform of fx of x, but then once you calculate, you have to get omega and replace it by minus omega. So the difference between characteristic function is that for characteristic function, you take Fourier transform and then you replace frequency by minus value of whatever it is. Basically, this is a moment. So you see that this is equal to mean of e to the power of j omega x. So this is one moment of your distribution. So characteristic function is obtained from fx of x, so anything, or from distribution. So this is why we call it a moment, because this is obtained from the distribution. It's one specific moment or gallons looking at the distribution, but because it is Fourier transform, we can, from the moment, we can get the distribution back. Now here, if you put omega equals 0, characteristic function fx of omega, if you put omega 0, will become mean of e to the power of j omega, which is 0 times x. So e to the power of j0 is equal to 1. So you get 1. So we have this property. Moreover, you can easily show that the supremum or the maximum of the absolute value of the characteristic function is always smaller than. So you could see, you can show that phi x of omega, its absolute value, is always smaller than the smaller than 1. Okay, the reason is this is easy to prove because this is equal to absolute value of integral whatever you have here, and you know that the absolute value of integral is always smaller than equal, so let's say this is dx, is always smaller than integral of absolute value of whatever you have here dx. Now, so here what we have e to the power j omega x fx of x, and absolute value of these is equal to absolute value of first one, which is 1, times absolute value of the second one, which is the function itself, because it's non-negative function. And this guy turns out to be integral of fx of x dx from minus infinity to plus infinity, and fx of x dx the total integral is equal to 1. So this is proven. So the sup, which means that this function is always smaller than this one. So this is for characteristic function, which is Fourier transform evaluated at your negative frequency. A moment generating function is basically the Laplace transform. The difference between Laplace transform is that in Laplace transform you have a minus sign, but historically statisticians they didn't put minus because statistic was independently developed. There have been some people who have worked in it, but they didn't put minus, and then they have been very reluctant to accept the minus, although putting the minus make things easy. So the moment generative function basically is to take Laplace transform of the PDF fx of x, and then replace s by minus s. So if you know Laplace transform, you can easily calculate the moment generating function. So here you see that this is g of x. So you could say that the Laplace transform phi x of s is equal to mean of e to the power of sx. So this is moments. The beauty of this one is that these can give you fx of x back. So it preserves all of the information about your PDF. So sometimes if I say this distribution, I can give you the moment generating function. So moment generating function gives you the full information about distribution. PDF gives you full information about the distribution. CDF also, because it has one-to-one relationship, fx of x about that. So sometimes if I give you the CDF, you can calculate PDF and then Laplace transform and get the moment generating function, and vice versa. So different ways to represent or give a distribution. So moment generating function. Why we call it moment generating function? Because it is easy to generate and calculate the moments using this function. You know that the moments of a random variable, let's say if I want to calculate mean of x of n, this is equal to integral from minus infinity to plus infinity of x to the power of n fx of x dx. So this calculates for me moment of order n, but you can calculate the moment of order n using moment generating function without integral. So this one needs an integration. In a moment generating function, you don't need to do integration, but you can do derivation, differentiation. So let's see how. So another function which is very helpful is the second characteristic function and second moment generating function. So if you take logarithm of this function, if you take ln of this one, logarithm of this one, a logarithm of the integral, I call it second characteristic function of distribution. So if you write the moment characteristic function, the expression of characteristic function in log domain, we call it second characteristic function. If you write the log of this one here, we call it second moment generating function. It is very useful to work in second characteristic function in some specific applications which are very useful. So instead of this integral, you can use these expressions, which are basically the same as those integrals. So these are just definition of moment generating function and characteristic functions.